lecture, this time about the Riemann-Hilbert correspondence over Fp.
All right, thank you very much. So let me just start by reminding you where we ended last time. So we were talking about the classical Riemann-Hilbert correspondence over the complex numbers. So if X is a smooth algebraic variety, there's some equivalence of categories where the right-hand side is this derived category of regular holonomic D-modules. That's something with a purely algebraic definition. And the left-hand side is something more topological in flavor. It references X with the analytic topology, meaning the underlying complex manifold of X. And it has something to do with constructible sheaves on that topological space. And so let me say a few words about this. So let X be an algebraic variety over the complex numbers. It has this underlying topological, sorry? It has this underlying topological space, and then you can study, for example, representations of its fundamental group over any field K that you like. And more generally, you can study sheaves of vector spaces on X, where the vector spaces are vector spaces over your favorite field K. And we say that a sheaf is constructible if we can decompose X into algebraic subvarieties X alpha such that the restriction to each X alpha is a locally constant sheaf or a local system. So this is a definition that you can make for any field K. And in general, it's something that that's defined using the analytic topology on X. Now, if K is the field of complex numbers, then this category of constructible sheaves is something that you can access in a purely algebraic way via the Riemann-Hilbert correspondence. But another thing that you could do is take K to be a finite field. And if K is a finite field, this category of constructible sheaves is something that you can access again in a purely algebraic way, but a different purely algebraic way. The category of constructible sheaves on this complex manifold, Xn, is equivalent to the category of constructible sheaves on X with respect to the Étale topology. And this is an equivalence of abelian categories. And more generally, there's an equivalence of derived categories between the category that you would define thinking of X as a complex manifold and the category that you would define giving X the Étale topology. So an example of a consequence of this is that if you want to compute the cohomology of that complex manifold with coefficients in a finite field, well, that's the same as the Étale cohomology of X. So that statement is usually called the Artin comparison theorem. So the upshot of this for us is that if K is a finite field, then the right-hand side of this equivalence is something purely algebraic in nature. It doesn't rely on the fact that we're working over the complex numbers. You can define Étale sheaves for varieties over any field you like, or more generally for any scheme. So if X is any scheme, you can look at sheaves of FP vector spaces with respect to the Étale topology. So they form a category, which I'm going to denote by sheaves X, comma FP. And the question that I want to ask in this lecture is whether or not there's some description of this category that you can give in quasi-coherent terms, something that relates these mod P Étale sheaves on X to quasi-coherent sheaves on X. And now for this to be sensible, we probably want the category of quasi-coherent sheaves on X to be a sort of p-torsion category. So I'm going to assume throughout this lecture that X is an FP scheme. So we're going to be very far away from the previous lecture where X was defined over the complex numbers. And let me just begin with a disclaimer. I'm going to be talking about Étale cohomology on schemes in characteristic P with coefficients in characteristic P. And that's not a good theory. That's an invariant that people typically don't want to consider for two reasons, or maybe for many reasons. But one is that there isn't a good theory of duality, like what you would think of as the analog of Poincare duality is not true in this setting. And another problem is that the answers typically are too simple. So like the cohomology of projective varieties ends up being smaller than you would expect it to be. And well, I'm going to say a few words about both of these points later on in this lecture, but in some sense, you can think of what I'm going to talk about as a quantification of the idea that Étale cohomology with FP coefficients is too simple. I'm going to tell you exactly how simple it is. So for the rest of this lecture, R is going to be a commutative algebra over FP, commutative ring where P is equal to 0. X is going to be the associated affine scheme. And we're going to make heavy use of the fundamental feature of mod P algebraic geometry, which is the Frobenius map. So that's the map from R to itself, which carries every element to its pth power. If we're in characteristic P, then that's a ring homomorphism. And it induces a map of schemes from X to itself that I'm going to denote by phi sub X. And what does this map look like? Well, at the level of topological spaces, that's just the identity map. It carries every point of X to itself. But it's not just the identity with respect to the Zariski topology, it's also the identity with respect to the Étale topology. So if F is any Étale sheaf on X, then F is isomorphic to its push forward along the Frobenius map in a canonical way. So the Frobenius map sort of doesn't change an Étale sheaf. And if you were interested in comparing Étale sheaves with quasi-coherent sheaves, you then might want to focus your attention on quasi-coherent sheaves that also have this feature. So let me introduce a definition. So here R is an FP algebra. A Frobenius module over R is an R module M with an additional structure. It's a map from M to itself that I'll denote by phi, and it's required to be Frobenius semilinear. That means that if you apply phi to lambda times X, you get lambda to the P times phi of X. And I'm going to say that M is a perfect Frobenius module if this map phi sub M is an isomorphism, meaning it's a bijective map of abelian groups. And so, well, an R module M is something that you can think of as a quasi-coherent sheaf on the scheme X. And giving it the structure of a Frobenius module is equivalent to giving a map from this sheaf into its push forward along the Frobenius. And saying that it's perfect is equivalent to requiring that this map is an isomorphism. Okay, so that's a definition. Where am I headed? Well, I want to compare p-torsion Étale sheaves on X with Frobenius modules over this ring R. I'm going to describe a particular construction that compares them, which is some joint work with Bhargav Bhatt. But of course, we're not the first people to think about this. There's a lot of constructions that are closely related to what I'm going to describe. So I've listed a few of the relevant names here, and quite likely I've missed some. So apologies if your name should be up here, and it isn't. And in particular, there's a construction of Matt Emerton and Mark Kisin, and I'm going to say a little bit about it at the end if we have time. All right, so in the previous lecture about Riemann-Hilbert correspondence over C, I started by thinking about the simplest case, which was complex varieties of dimension 1. I didn't bother talking about complex varieties of dimension 0 because in some sense there's nothing to say there. But if we're working over a non-algebraically closed field, it's no longer true that there's nothing to say for varieties of dimension 0. Étale sheaves can be interesting when X is the spectrum of a field, at least if that field is not algebraically closed. So let's fix an algebraic closure of K, and let me write G for the Galois group. This is a profinite group. And in this setting, the theory of Étale sheaves can be made more concrete. The datum of an Étale sheaf of FP vector spaces on X is equivalent to the datum of a vector space with a continuous G action. Continuous means that the stabilizer of any vector is an open subgroup of G. And well, the constructible sheaves correspond under this dictionary to the finite dimensional representations. So let's talk about the case where K is a field of characteristic P. I'll again write G for its Galois group. And if K is perfect, there's a theorem of Katz, which gives an equivalence of categories from this category of finite dimensional representations of G over FP to the category of perfect Frobenius modules, which are finite dimensional over K. So let me describe this equivalence both directions. So I'll write V for the Galois representation and M for the Frobenius module. So given a Galois representation, you can tensor it over FP with K bar. That's then a vector space over K bar with an action of the Galois group G. And then you can take the the Galois invariance to get a vector space over K. And that's equipped with the Frobenius map, which is induced by the Frobenius map on this ring K bar. There's a construction that goes in the other direction. If you start with the Frobenius module over K, you can tensor that over K with K bar, and then take the elements that are fixed by the Frobenius. So that is then a FP vector space having an action of the Galois group coming from the action on this field K bar. And the content of the theorem is that these constructions are mutually inverse, and they give you a way of passing back and forth between Galois representations and Frobenius modules. And the key point is that neither of these constructions loses information. If you input an n-dimensional vector space, the output has the same dimension. So if V is a finite dimensional representation of G, what we're saying is that when you tensor with K bar, you can find a basis for that as a K bar vector space of vectors that are invariant under the Galois group. And that's a statement that essentially you can think of as a part of Galois theory. It's a very general statement. And in the other direction, it's something that's more specific to the current situation. If you start with a finite dimensional perfect Frobenius module and you tensor it with K bar, then you can find a basis for that, again, over K bar, consisting of vectors that are invariant under the Frobenius. And that's essentially what you have to check in order to prove this theorem. Okay, so this was a theorem about finite dimensional representations. And now I want to remove the finite dimensionality. So same setting, K is a perfect field of characteristic P. On the Galois representation side, there's essentially no issues thinking about infinite dimensional representations. They're just always the union of their finite dimensional subrepresentations. But in the setting of Frobenius modules, that is not true. A Frobenius module is generally not going to be the union of Frobenius submodules that are finite dimensional when regarded as vector spaces over K. And there's a canonical example to think about. So take the free K vector space generated by symbols E sub I, where I is an integer, and you can make that into a Frobenius module, even a perfect Frobenius module, by declaring that the Frobenius takes each EI to EI plus 1. And this is an infinite dimensional Frobenius module, which has no finite dimensional Frobenius submodules other than 0. So I want to rule out this behavior. So let me introduce one more definition. So I'm going to work over a general FP algebra R. I'm going to say that a Frobenius module M is algebraic if, first of all, it's perfect. Remember, that means that the Frobenius is a bijection. And secondly, I'm going to demand that every element of M satisfies an equation, or the Frobenius on that element satisfies an equation, meaning that phi to the n of x can be written as a linear combination of x, phi of x, and so forth through phi n minus 1 of x. And another way of saying this is that it rules out the behavior on the previous slide, namely M can be written as a union of Frobenius modules which are finitely generated over R. So with that terminology, let me just restate Katz's theorem without the finite dimensionality assumptions. So K is a perfect field. You can look at representations of its Galois group over the field FP, and these are identified now with algebraic Frobenius modules over K. And the constructions in both directions are implemented exactly as before. The point is that by imposing this algebraic condition, I've guaranteed that all the action is happening on finite dimensional subspaces on both sides. Okay, so this is a theorem. And the theorem that I would like to talk about today is just a generalization of this. We're just going to remove the assumption that K is a field. So let R be any FP algebra, let X be the associated affine scheme. There's an equivalence of categories between p-torsion Étale sheaves on X and algebraic Frobenius modules over the coordinate ring R. And when R is a perfect field, this is exactly the theorem of Katz that I stated on the previous slide. So the first thing that I would like to do is tell you how this equivalence is given, at least in one direction. So let R be an FP algebra as usual. Let M be a Frobenius module. And I'm going to write M tilde for the associated quasi-coherent sheaf, meaning M tensored over R with the structure sheaf of X. With the caveat, I'm thinking of that as happening in the world of sheaves on the Étale side of X. So M tilde is an Étale sheaf. If M is a Frobenius module, then that Frobenius gives you a map from M tilde to itself. And then I want to look at the subsheaf of M tilde consisting of things that are fixed by that Frobenius map. I'm going to denote that by de Rham of M, by analogy with what happened in the previous lecture. So that's an Étale sheaf, which is just defined to be the kernel of the identity minus Frobenius as a map from M tilde to itself. And an example to keep in mind is the case where R is the spectrum of a field. In that case, you can think of the output here, an Étale sheaf, as a Galois representation. And then this is exactly the construction that appeared in Katz's theorem. You input a Frobenius module M, and you output a Galois representation, which is given by taking M, tensoring it with the algebraic closure, and taking the fixed points of Frobenius. So now let me just restate in a more precise form this theorem that I mentioned earlier. X is spec R, then this construction, taking Frobenius module to its de Rham sheaf, well, it's a construction that you can define for any Frobenius module at all, but I want to restrict it to the algebraic Frobenius modules. And on algebraic Frobenius modules, it gives you an equivalence of categories with the category of p-torsion Étale sheaves.
Did you tell us already what algebraic means in this generality?
Algebraic means that it's perfect and every element satisfies the Frobenius satisfies an equation. Okay, so let me just bring out the analogies with what happened last time. So last time we were working over the complex numbers, now we're working over FP. Last time X was a smooth algebraic variety. In this setting, X is an arbitrary FP scheme, although I'm assuming just for simplicity that it's affine. We can consider in both settings quasi-coherent sheaves. In the affine case, that's the same data as an R module M. And we can consider quasi-coherent sheaves equipped with certain additional data. So in the previous lecture, that was the extra data was a flat connection. As we were studying algebraic D modules, here we're studying Frobenius modules, R modules that are equipped with some kind of Frobenius. Now, in both settings, you can think about quasi-coherent sheaves as living on X equipped with the Zariski topology, but there's some finer topology that we want to consider. So on Tuesday, that was the analytic topology, thinking of X as a complex manifold. Today, it's the Étale topology of X. And then there was a construction which took quasi-coherent data and make it into a sheaf on this with respect to this finer topology. So you can take a quasi-coherent sheaf E and make it into a sheaf of modules over holomorphic functions. Here, that's this construction M goes to M tilde. And then you can you have these additional structures that I already mentioned, and you can use them to extract an appropriate subsheaf. So on Tuesday, that was the sheaf of sections of the holomorphic bundle that are flat with respect to the connection. Here, it's sections of M tilde that are fixed by the Frobenius. And well, that's a construction that you can do in a lot of generality, but there are some particular inputs where this construction will behave particularly well. On Tuesday, those were the regular holonomic D modules, and today they're the algebraic Frobenius modules. So now there's an objection that you might raise to these analogies here, because on Tuesday, I told you that the construction that implemented the Riemann-Hilbert correspondence, it was really a construction in homological algebra. You took an algebraic D module and you assigned to it not just a sheaf, but a complex of sheaves, this holomorphic de Rham complex. There's something like that that you could do here too. It's much simpler. Just to a Frobenius module, you can assign to it what you might call its Artin-Schreier complex. So that's just a two-term complex having a copy of m tilde in degree 0, a copy of m tilde in degree 1, and the differential is the Artin-Schreier map, the identity minus the Frobenius. So you could consider this whole complex, but if you want to stick to algebraic Frobenius modules, you don't have to. That is, this complex a priori, there might be some cohomology in degree 1, but actually there isn't. If M is an algebraic Frobenius module, there's an exact sequence of Étale sheaves given by this de Rham sheaf going to m tilde, going to m tilde. So what's the upshot of this proposition? What does it buy you? So let's be in our usual setting. And let F be an Étale sheaf on X. And suppose that we know that F comes to us as the de Rham sheaf of an algebraic Frobenius module M. So then what I told you on the previous slide is that you have an exact sequence of Étale sheaves. F is the kernel of this Artin-Schreier map from m tilde to itself. And in general, if I give you an exact sequence, short exact sequence of sheaves, there's a long exact sequence of cohomology groups. But in this particular example, that's particularly simple, because m tilde is a quasi-coherent sheaf and X is an affine scheme. So m tilde, the cohomology in degree 0 is just the module M that you started with, and the cohomology in higher degrees is 0. And as a consequence, you can just read off the Étale cohomology of X with coefficients in F. And you learn that in degree 0, you see the kernel of the Artin-Schreier map from M to itself. In degree 1, you see the co-kernel. And you get 0 in all higher degrees. So this is something which is very familiar when F is the constant sheaf with values Fp. How do you compute Étale cohomology with mod p coefficients on an Fp scheme? You use exactly a sequence like this, and the answer comes out very simple for exactly this reason. And so in some sense, what I'm telling you is that that's not just a story for the constant sheaf, that's a story for any p-torsion sheaf on an Fp scheme X. There's something like the Artin-Schreier sequence that you can use to compute its cohomology. And to know that, what you need to know is that your Fp Étale sheaf F can be written as the de Rham sheaf of an algebraic Frobenius module M. And the content of the Riemann-Hilbert correspondence is exactly that you're allowed to do that. That is, given F, there's an essentially unique M for which this story plays out like this. Okay, so let's talk about that. All right, so I told you that there's this equivalence of categories implemented by the de Rham functor, and saying that something is an equivalence of categories means there's a functor in the other direction. So I'm going to denote that by RH. So it's a functor that goes from the category of p-torsion Étale sheaves and identifies it with the category of algebraic Frobenius modules. I'm going to call this the Riemann-Hilbert functor because I want to think of it as solving a characteristic p version of the Riemann-Hilbert problem that we talked about on Tuesday. So the input to this functor is data of a topological type, constructible sheaves, or more generally arbitrary sheaves on the Étale side of X. So that includes things like representations of the fundamental group of X. And then it produces output quasi-coherent data, which in this case means R modules with an extra structure of a very specific type. And so if you want to use this as a tool, like for example, if you want to use the previous slide, this Riemann-Hilbert functor is giving you a mechanism for computing Étale cohomology with coefficients by something like the Artin-Schreier sequence. Then you want to know how this functor works. What does RH look like? So let's start simple. In the case where R is a field, this is already given to us by the proof of Katz's theorem. Right? Katz's theorem was the Riemann-Hilbert correspondence over the spectrum of a perfect field, and the proof involved just explicitly writing down the functors in both directions. And so what's the formula that you get there? Well, if you have an Étale sheaf and you think of it as a Galois representation V, then this Riemann-Hilbert functor assigns a Frobenius module, which is just obtained from V by tensoring with K bar and taking Galois invariance. So you could ask, is it given by a procedure like this in general? So now what's essential here for this description is not really that R is a field. What's essential is that F is a locally constant sheaf. So that's something that's automatic if R is a field and F is constructible. But more generally, if F is locally constant, then the Riemann-Hilbert functor is given by a formula very much like this. Namely, you take F as an Étale sheaf, you tensor it with the structure sheaf of X, and then you take global sections to get a Frobenius module. But this is not the construction that you want to give in general. If F is not a local system, but a sheaf with some kind of singularities, then this formula is not going to be correct. And so this work, we proved this a few years ago, and I gave some talks on it back then. And something that I always mentioned then was we don't really know a formula for it in general. That is, our proof that this was an equivalence of categories, it involved in some sense constructing this Riemann-Hilbert functor. In other words, solving some kind of Riemann-Hilbert problem. But the way that we solved it was a little bit like the process that we went through on Tuesday. If you want to define RH of F, if F is a constructible sheaf, well, there's some big open set on which you know what to do, but then you have to figure out how to extend to the boundary. And then maybe you fiddle around with some kind of local constructions that you then need to glue together. And the end result is you get something not very explicit. But a few months ago, Akil Matthew gave another proof of the Riemann-Hilbert correspondence. And his proof actually came with a formula for this Riemann-Hilbert functor. The Riemann-Hilbert of F, as an abelian group, it's an X group. It's the group of extensions of OX by F. But the fine print is this extension is being computed not in this, the category of Étale sheaves on X, but in the category of Étale sheaves on the big site of X, meaning that you have to think about not just about Étale X schemes, but you have to think about bigger X schemes in order to compute this X group. Okay, so if this looks a little mystifying, let me demystify it a little bit by explaining what that X group would have to do with this de Rham functor that I defined earlier. So let's say M is an algebraic Frobenius module, and then I told you that in that case you have an exact sequence of Étale sheaves given by Artin-Schreier theory. And now let's suppose that you have an element of this Frobenius module M. That's something that you can think of as a map of quasi-coherent sheaves from the structure sheaf into M tilde. And then given that, you can pull this short exact sequence back and construct something which is an extension of OX by this de Rham sheaf. Now, that's a construction which depends on X. And what it gives you is a homomorphism from M into this X1 of OX by that de Rham sheaf, which is, by this formula of the previous slide, what you get by composing the Riemann-Hilbert functor with the de Rham functor. And now, from this point of view, what is it that you have to do? Well, you want to prove that this map is an isomorphism. In other words, you want to show that every extension of OX by de Rham of M has to come from this construction applied to a uniquely determined element of M. And if you prove that this map is an isomorphism, you're a little more than halfway done with the proof of the theorem. You've given functors going in both directions, and you've checked that one of the compositions is the identity. Now, in order to prove this is an isomorphism, you have to compute some X group. And as long as you're computing X groups, you might as well compute all the others. And associated fact here is that all the other X groups vanish. X1 is the only interesting group here, which is in essence why we're getting an equivalence of abelian categories and not an equivalence of derived categories. So this is a description of this Riemann-Hilbert functor. In some sense, it's completely explicit. I've told you what that abelian group is. It's something with a name, but it might not be so helpful in a practical situation when you actually want to figure out what it looks like. You'd have to compute X groups on this big site. So let me tell you some properties that this Riemann-Hilbert functor has that might be more useful if you just want to get a feel for what it's doing. So for simplicity, I'm going to start with the case where R is a perfect FP algebra, meaning every element of R has a unique pth root. And well, the first thing is this Riemann-Hilbert functor. If you apply it to the constant sheaf, you just get R. It preserves tensor products. So if you apply the Riemann-Hilbert functor to a tensor product of sheaves F and G, you get the tensor product of those R modules relative to R. It also behaves well with respect to base change. So if S is a perfect R algebra, that gives you a map of affine schemes from spec S to spec R. And if you have a sheaf on spec R, you could pull it back to S and apply the Riemann-Hilbert functor. That'll give you some Frobenius module over S. And that can be computed by first applying the Riemann-Hilbert functor over R to get a Frobenius module over R and tensoring over R with S. Some compatibility with pullback. There's also a more limited compatibility with direct images. If S is a finite R algebra, for example, if S is a quotient of R, well, an Étale sheaf on spec S gives you an Étale sheaf on spec R. And if you want, by pushing forward, and if you want to apply the Riemann-Hilbert functor downstairs, you can, that's the same as the Riemann-Hilbert functor that you compute upstairs. So this is behavior that you see when the ring R is perfect. But of course, that's an assumption you might not want to make. Like maybe you're interested in characteristic P algebraic geometry. The interesting R's are where R is the coordinate ring of an algebraic variety. Those will essentially never be perfect. If R is not perfect, you have essentially all the same statements. The only difference is you replace R by its perfection everywhere. So if you take the constant sheaf on X, apply the Riemann-Hilbert functor, you get not R, but its perfection. Tensor products of sheaves go to tensor products of, but computed not relative to R, but relative to the perfection, and so forth. So these formal properties, essentially, you can use this to figure out what the Riemann-Hilbert functor looks like, at least in a lot of cases. So let me give an example, which I think is very instructive. So let's R be an FP algebra, and now suppose I give you an element T. And writing X for spec R, this element T breaks X up into two pieces. There's an open subset where T is invertible, which I'll call U, and a closed subset where T vanishes, which I'll call Y. And there's an associated decomposition of the constant sheaf on X. It sits in a short exact sequence where it has a subsheaf which is extended by 0 from U, and a quotient sheaf which is extended by 0 from Y. So this is an exact sequence of Étale sheaves. You can apply the Riemann-Hilbert functor, and you get an exact sequence of Frobenius modules. Now, I told you what happens in the middle. If you take the Riemann-Hilbert functor and apply it to the constant sheaf, you get the perfection of R. And I is a closed immersion. It's compatible with the Riemann-Hilbert functor. So you also know what happens on the right. You'll get the perfection not of R, but of R mod T. And from the exactness of this sequence, you can read off what the Riemann-Hilbert functor is doing to this sheaf that's supported on U. It just assigns to it the kernel of this quotient map. That's an ideal inside of the perfection of R. It's the ideal generated by T and all the P power roots of T. All right. And so maybe I should mention that in our original approach to the theorem, when we didn't have a formula for the Riemann-Hilbert functor, a lot of the hard work was just constructing it, meaning proving that there exists something with a certain universal property. And it was somehow always reduced to this case. This is was essentially the guiding principle for how you figure out what this Riemann-Hilbert functor looks like. All right, so how much time have I got left? What's that?
Until 3.
Until 3. Oh, wow, that's a ton of time. OK, so what I would like to do with the rest of this lecture is talk a little bit about how this construction is related to an earlier construction of Matt Emerton and Mark Kisin. So they also proved some version of a Riemann-Hilbert correspondence relating constructible sheaves on a smooth variety and characteristic P to some kind of Frobenius modules. But the kind of Frobenius modules they were interested in were a little bit different. So let me first consider a general situation, let R be any FP algebra, and let M be an R module, and I'll write M tilde again for the associated quasi-coherent sheaf. So we've been talking about Frobenius modules, meaning that M is equipped with a Frobenius semilinear map, phi, from M to itself. And you can think about this in the language of quasi-coherent sheaves. I said earlier, you can think about the data of this map as a map of OX modules from M tilde to the Frobenius push forward of M tilde. But another way you can think about it is that you have a map from the Frobenius pullback of M tilde to M tilde. Those data are interchangeable with one another. And we've been talking about perfect Frobenius modules. Frobenius module is perfect if this map alpha is an isomorphism of quasi-coherent sheaves. But another condition that you could consider is the condition that M is unit, meaning that beta is an isomorphism of quasi-coherent sheaves. So this is something that feels a little bit more like the theory of D modules. So first, let me remark that unit Frobenius modules, they're not such a good idea unless you make some assumptions about the ring that you're working over, right? Assumption like that R is a regular ring, that guarantees that the Frobenius map is flat. So for example, a kernel of a map between unit Frobenius modules will also be a unit Frobenius module. That's something which is not clear in general, but is true if R is nice. And so the main example to think of is when R is the coordinate ring of a smooth variety over field K. And in that case, well, this pullback along the Frobenius, it gives you a functor from quasi-coherent sheaves on X to quasi-coherent sheaves on X, but it actually lands in quasi-coherent sheaves having a little bit of additional structure. Namely, the pullback of any quasi-coherent sheaf along the Frobenius always has a flat connection. And this is a fully faithful functor whose essential image can be characterized. These are the sheaves with a flat connection having vanishing p curvature. So for our purposes, the definition here is not important. What I want to remark is that if M is a unit Frobenius module, then the associated quasi-coherent sheaf in this setting always has a flat connection. The reason being, it is the Frobenius pullback of something else, namely it's the Frobenius pullback of itself. So unit Frobenius modules are a very natural object that you want to consider if you're looking for some characteristic P analog of having a connection. Okay, so now let me mention the result of Emerton-Kisin. So they're setting X is a smooth variety over a field. They actually don't assume that the field is perfect. And they construct a fully faithful embedding from the derived category of constructible p-torsion sheaves on X into the derived category of Frobenius modules. It's a contravariant embedding this time. And they describe the essential image as complexes whose cohomologies are what they called locally finitely generated unit. So this unit condition is the one that I mentioned earlier. It's saying that a module is its own pullback under the Frobenius, and locally finitely generated is some finiteness condition in that context. So it's natural to ask what this has to do with what I've been talking about in this lecture. So let me just first emphasize these constructions are not the same. One obvious difference is that the functor I described as a covariant functor, their construction is a contravariant functor. Their construction is contravariant because at some point they're involving some kind of duality, and as a consequence, for their construction to be well behaved, they need to impose some finiteness conditions. So the construction I described is defined on arbitrary sheaves, and theirs is really in the setting of constructible sheaves. Now the construction that I described, it's an exact functor between abelian categories. You can, if you like, extend it to an equivalence of derived categories, but the essence of what's going on is already visible at the level of abelian categories. But their construction feels a little bit more like the Riemann-Hilbert correspondence over the complex numbers, where it's not T exact with respect to the obvious T structures. It's really a functor between derived categories. And remark is our construction, it's something that you can do for any FP scheme X. Here I was assuming that X was affine, but that's an assumption that's easy to remove. whereas they were assuming that X is a smooth variety. And the importance of that assumption is essentially it guarantees that the Frobenius map is flat, so the theory of unit Frobenius modules behaves well. And let me remark that assumption can be removed. Well, I'll say a little bit more about this in a second. So I think to get a feel for how these constructions are different and what they're doing, it's instructive to go back to this example where R is an FP algebra. I'm going to assume that it's a smooth FP algebra to be in the setting of Emerton and Kisin, and let T be a non-zero divisor inside of R. And then, as before, that element T, it decomposes the spectrum of R into two pieces, an open subset U where T is invertible, and a closed subset Y where T vanishes. And you have an exact sequence of Étale sheaves associated to this picture. And if you apply the Riemann-Hilbert functor of this lecture, you get a short exact sequence of Frobenius modules that we worked out earlier. In the middle, you have the perfection of R. On the right, you have the perfection of R mod T. And on the left, you have whatever you have to have, some ideal inside the perfection of R. And now what happens if you apply the Riemann-Hilbert functor of Emerton-Kisin? Well, that, first of all, it's a contravariant functor, so you get maps going in the opposite direction. And it lands in the derived category rather than in the abelian category of Frobenius modules. So rather than giving a short exact sequence, it gives a distinguished triangle in the derived category. What you get in the middle is the ring R itself. What you get on the left is R with T inverted. And what you get on the right is something that's not concentrated in degree 0. It's a cohomological shift of some quotient. And this distinguished triangle is obtained by rotating a short exact sequence in the abelian category, namely R going to its localization, going to whatever the co-kernel of that map is. So, if you're familiar with the way algebraic D-modules work, this Emerton-Kisin correspondence probably looks a lot more familiar. This idea of taking an ideal and forming its perfection is much more a sort of characteristic P idea. Okay, so these are two different constructions, but they're related. So there's a commutative diagram that they fit into. So let's restrict to the constructible derived category of Étale sheaves so that both of these functors are defined. So the Riemann-Hilbert functor and the Emerton-Kisin version both are fully faithful embeddings into some derived category of Frobenius modules. And they are interchanged by a certain operation that you can describe directly in the world of Frobenius modules. I'm going to denote it by D. It's some kind of duality, and there's a dotted arrow there to indicate that it is only partially defined. But this is something that you can read off of the definitions, essentially. And using this, you can really recover either version of the Riemann-Hilbert correspondence from the other by understanding this how this duality functor behaves. And a consequence is you can extend the Emerton-Kisin version to the setting where X is not a smooth algebraic variety. In settings where the Frobenius map is not flat, you again obtain a fully faithful embedding into some derived category of Frobenius modules, but to describe the essential image, you can't work at the level of individual cohomology sheaves. You have to impose some conditions at the derived level. Now, the way that I think about this is, well, one of the things I mentioned early on is that the category of p-torsion sheaves on a scheme in characteristic P, it's not a good theory. One of the things that's wrong with it is it doesn't have a good theory of Verdier duality. There's no good notion of Verdier duality for constructible FP sheaves, but even though there's no duality on the FP sheaves, there is some kind of duality on the category of Frobenius modules, and there's two different embeddings from constructible FP sheaves into this category of Frobenius modules that are in some sense dual to each other. So I think of this this D here that appears here as some counterpart of Verdier duality in this setting, which it exists at the level of Frobenius modules rather than at the level of constructible sheaves. And I think that is all that I've prepared for today. So thank you very much.